Hey, there's something different about power series in the complex plane, which is that the convergence region for a power series is a disk, and that opens up some possibilities that don't happen in the real numbers. And what I want to do is just look at log and look at some Taylor series to illustrate that. This is why you're interested in compactness. And so this is a kind of a motivational thing and a little bit of review about Taylor series. So let me start in um, assuming that you know the general way that Taylor series go. I'm going to say that I've got my function natural log of z, and I just start taking derivatives, and those go the same as um, in real analysis. So the first derivative is 1 over z. The second derivative is minus 1 over z squared. The third derivative is plus, because the signs are negative. And now we have 2 times 1 over z cubed. Now, I'm not a normal person, so I don't do any multiplications until I need to. And 2 times 1 is 2, but you're going to lose the pattern. So leave it as 2 times 1. The fourth derivative, usually that's enough, is minus 3 times 2 times 1. The new factor was a minus 3, and that's over z cubed. And I seem to have picked up an extra. Oh, it's over z to the fourth. That's why. My mistake. Okay. Z to the fourth. I know it can't be your mistake. I'm here by myself, except maybe for my dog. Anyway, okay. So those are the basic things that go into the Taylor series. Now you have to divide each of those by n factorial to get to the z to the n term, and evaluate. Well, you're going to have z minus the center point, and so that's the deal. So let me draw you a little picture that's going to show what's going to happen. This shouldn't be a surprise. You already know this, but it's not. It's I don't know that it's a surprise, but it's something that is a big difference between the real case and the complex case. So if you do this around z equals 1, and we'll do this. You're going to do write out the Taylor series and do the ratio test will do it, and that'll tell you that you have convergence inside that disk where z is less than 1, not on the boundary, but where z is less than 1, you have convergence. And so that will be the Taylor series around 1. But now we have a different option, and so what we can also do is take the Taylor series around I. And so I've drawn I in here, and just to kind of this is a rough picture. My apologies. And so there's the region of convergence around I. That's going to be the same as you'll see when we do the ratio test for this one. And what's interesting here, and something that you may not have been expecting, is that there's an overlap where you have two different ways of calculating natural log of z. You can say, hey, I'm going to do this using the one way, or I'm going to use this doing the I way. So it's the I way or the one way. And that's a big difference over what happens in the real numbers. In the real numbers, as you look at as you change the center, the radius of convergence grows with the center, and so it always goes up to 0 where the natural log is not defined, so it couldn't possibly converge there. So the general thing with a Taylor series, let me write out the general form. You take the nth derivative at some point a, and you divide by n factorial, and then you multiply that by z minus a to the n. And some people might give you some arguments about this because it's infinite, but this is a power series. You're going to have a z term, you're going to have a z squared term, you're going to have a z cubed term, you're going to have all these terms. It might be difficult to write them down, but that's a power series, and so there's the deal. So when we do this around 1, what we're going to have to look at is f of 1, f prime of 1, f double prime of 1, and let's go to the third derivative and see what happens, and I am going to simplify that. F of 1 is 0, that's natural log of 1. F prime of 1 is 1 over 1, that's 1. F double prime of 1 is minus 1 over 1, that's minus 1. And F triple prime is 2 over 1, 2 times 1 over 1. And so forth and so on. And so the series that you get looks like this. You're going to get an n minus 1 factorial on top. That comes from taking these derivatives of 1 over z, and an n factorial on the bottom. And so n minus 1 factorial divided by n factorial is just going to be n. So what you get here in the final consideration is minus 1 to the n minus 1. This is the top of each term, z minus 1 to the n divided by n. Now it's pretty clear if you do the ratio test to this converges if absolute value of z minus 1 is less than 1. So there it is. That's why I've drawn this green circle here. That's the convergence for the 1 series. Now if we do the I thing, that's kind of a little funkier. So if we look at f of I, that's natural log of I. That's a thing. And f prime of I is 1 over I. Normal people call that minus I. F double prime of I is minus 1 over I squared. Normal people call that 1. I squared is minus 1. That's on the bottom. And f triple prime of I is 2 times 1 over I cubed. Well, normal people call that minus 2 factorial over, minus 2 factorial times I. I cubed on the bottom is minus I, which is I on the bottom, minus I on the bottom, which is I. So you end up with a series that looks like this. It's the sum, and things are very much going to be the same. Actually, let me not write it as a sum. Let's do it term by term. What you're going to get is I, natural log of I, and then you're going to have minus I times z minus I, because we've moved the center of the series to I. And then the next term is 1 over 2 factorial z minus I squared, and so forth and so on. So you've got a different Taylor series for what goes on around I. And so there it is. You have a Taylor series based at 1. You have a Taylor series based at I, and they overlap. And that is the big difference in terms of complex analysis versus real analysis. We're interested in power series. All the functions that we're going to do can be represented by power series. So these Taylor series are very important. But now we find that the regions can overlap if we do this series at different places. And so this is why you're interested in compactness. What's going on? If you remember correctly, compactness says that every open cover of some set has a finite subcover. So what happens is you take some complicated function over some complicated subset of the complex plane, and you do the Taylor series, do the Taylor series, do the Taylor series, do the Taylor series around every point in that domain. Holy smack, that's a lot of Taylor series. No, it's compact. You only need to use a finite number of those series. And this is why compactness becomes so important, because it replaces an infinite process with a finite process. So as you study the point set topology part of the plane, this is the motivation. This is why we want to do it, because of this change in the nature of power series between the real line and the complex plane.